Hey everybody. Today we're starting back the 2021 Spring Math MCAS. We're going to start with number 13. There's a digital version in the video description as well as a PDF that's printable, and that's what we're writing off of right now. This is a four-parter. We'll see how long this one takes. This might be a single problem video. It depends on how long it takes to go through this problem. All right, so let's get started. It says this question is 4 parts. Nora, Owen, and Peyton are studying expressions. Part A, Nora writes this expression, square root of 3 squared. What is the value of Nora's expression? Show or explain how you got your answer. So what you're going to want to do is write this out. So let me just get my color mark pen here. So radical 3 squared would be radical 3 times radical 3. And any radical times itself will give you the number inside the radical. Or any square root times itself will give you the number inside the square root. So the answer would be 3. And the tricky part with this is when you're doing this digitally, you'd have to show your steps. You'd have to type this out in the box to show how you got here. And it can take a little bit of practice. That's why it's so important that we train ourselves before we take this test. We use the digital platform. We get familiar with the keypad, the symbols, all that. So I hope that everybody watching this video is taking the time to work their way through these problems online as well, if you really want to give yourself the best chance of doing well on this test. Which everybody should. If you're taking the time to watch these videos, I'm going to assume that you are putting the time in to do well. And I think anybody that puts time into this test will pass it, in my opinion, based on my experience. All right, part B. Owen writes this expression, the cube root of 2 to the 6th power. What is the value of Owen's expression? Show or explain how you got your answer. So, okay, we're going to do something very similar. We're going to type this out. So we're going to start with, put it over here, the cube root of 2 to the 6th power, and that's going to be the cube root of 2 times 2 times 2 times 2 times 2 times 2. There should be 6 2's here, so 1, 2, 3, 4, 5, 6. Okay, now because this is a cube root, we're looking for numbers that happen more than, not just twice, but 3 times, because it's a cube root. So there's 3 2's here, and there's 3 2's here. So for each trio of a term, we're going to put a single term on the outside. So this is actually a perfect cube. So this is all gone. There's going to be 2 of them on the outside because there's two trios here. So it'll be 2 times 2, which of course would be 4. And that would be the solution for part B. Okay, so we're just simplifying radicals here, essentially. Okay, so it says part C, Owen writes a second expression in this form. And this is number 13, is it? Yeah. 13 continued. Owen writes a second expression in this form, radical x. What value should Owen use use for x to make his second expression equivalent to his first expression? So the first expression was equivalent to 4. If we go back to here, Owen's first expression turns out to be 4. Okay? So what value should Owen use for x in order to make this equivalent to the first one? So in other words, we're going to set this equal to 4. Okay, so I'm going to zoom in here. So I say radical x is equal to 4, and we're going to solve for x. So how do we solve for x? Well, we want to square both sides. That means we're going to get, this would be just x, and 4 squared would be 16. And that's it. Pretty straightforward. I guess there'd be another step in here. We'd actually say this squared and 4 squared, and that's what I should have written it like that. There you go. Pretty straightforward. But you can't get this part correct unless you get the part B correct. So it's dependent upon getting part B correct. All right, part D. Peyton writes a different expression that contains a cube root and an exponent. Peyton's expression is equivalent to Nora's expression. So Nora's expression was the first one, I believe. Yep, so Nora's expression was equal to 3. So this one's, okay, so part C was dependent upon B being correct. Part D is dependent upon part A being correct. Peyton's expression is equal to Nora's expression. Write an expression that could be Peyton's expression. Show or explain how you got your answer. So yeah, this one's interesting. I remember this one. I did this one, but mostly a little under a year ago. So okay, we know it's going to be equal to 3. And we know it's going to be a cube root and an exponent. So I'm going to write a cube root and an exponent. So here's the thing. Any cube root I raise to the third power will just be the thing inside the radical. So pretty straightforward. If I say this, like because I want it to be equal to 3, the cube root of 3 cubed would just be 3. Like if I simplify this, it would be 3 equals 3. So that would actually fulfill the requirement. So the expression I'm going to write is going to be this. It's going to be the cube root of 3 raised to the third power. Because if I simplify that, I'm going to get 3, which is what I found in part A. So this part I think could give people a really hard time if they don't really understand how cubes and exponents work. We want to know that we were told we need to include a cube root and an exponent. Not specifically what kind of exponent, but this just makes it way easier. There's a bunch. I mean, there's infinite ways you could write this, but in my opinion, this is the easiest way to do it. That'd be your answer there. Okay, let's continue. Number 14. Zoom out a little bit here. Okay. Okay, now we're looking at part 14. So number 14 says the table shows some values of the function f of x. Okay. Which of the following best describes f of x? A linear decay, a linear growth, an exponential decay, and exponential growth. And this one looks confusing, but not too bad. Here's the thing that's a little weird. The x values are going up by 3 here, and then up by 2. So it's not 0, 1, 2, it's not 2, 3, 4, it's 0, 3, 5. So the x value went by 3, and then it went up by 2. So it's a little harder to figure this out. What you have to do is, you're trying to see if whether or not the functional value is changing by the same amount each time. If it is, it's linear. If it's not, it's nonlinear. So let's see. What you can do is find out how much this difference is. Let's do 104 minus 13. Let's see what the difference is for the functional values from 0 to 3 here. So I'll put my calculator. So 104 minus 13, and that's going to be 91. So the functional value changed by 91, and then the x value changed by 3. So if I divide that, 91 divided by 3, that means it went up by 30 and a third, okay? So 30.3 repeating. That was the rate of change here, okay? So let's see what it is here. So this is 2, the x value is 2, well, x changes 2, the y changes, whatever this is. Let's figure what that is. So 416 minus 104. Oops, it's not right before, there you go. So let's do that. So 416 minus 104, that should be 312. That's over 2 because the x changes 2. So we have 312 over 2, which is 156. So you can see, it's definitely a nonlinear rate of change. There's a significant increase in the rate of change from here for the second interval here. So it's definitely nonlinear. So we're getting rid of both these. Okay. That means it has to be one of these exponentials. Now, a decay means the functional value is decreasing over time, and the growth means the functional value is increasing over time. So if you look at the functional value, right, which is actually the y, but the random f of x, which is fine, it's increasing. So clearly, it's an exponential growth. Okay, not too bad. Okay, now let's look at this one. Which of the following equations models f of x? So there's a real straightforward way to do this. One, we know it's exponential, so we can already knock a few of these out. This is non-exponential, so get rid of that one. This is linear, that one, so get rid of that one. So it's one of these two, okay, because you know it's exponential. And even if you don't have a lot of experience with exponential functions, you know these are linear. So just knock out the linear ones, and now you have a 50-50 shot at getting this correct. And what you can do, what I would recommend, is say, hey, I know the y-intercept is 13. So I know when the x value is 0, it's crossing the y-axis at 13. So if the y-intercept is 13, I should be able to plug in 0 for x over here and get 13. That's another thing you could do too. Now the problem with that is if you plug in 0 here, you're going to get 13. But if you plug in these other values, you're going to knock these out. That's another way you could do this. If you plug in all these values for all these functions, it's only going to, all three of them will only work with one of these. Okay, but that will take a significant amount of time to do that. But you could just say, I'm going to plug these in for x, 0, 3, and 5, and see if I get a true statement. A and C will definitely get knocked out pretty quickly. Although A would pass the first test because 0, 13 would work. So if you're not comfortable with exponential functions, you could always just plug these in. Again, you could do that, but I'm showing you a quicker way to do it. We do know it's going to be one of these two because these are linear, these are exponential. It's going to be one of the exponentials. I'm going to plug in 0. If I plug in 0 here, right, anything to the 0 power is 1, so 13 times 1, and that, of course, would be 13. If I plug in 0 here, we're going to get 91 times 2 to the 0 minus 1 power, and 91 times 2 to the negative 1 power, and 2 to the negative 1 power is just 1 over 2, so it'd be 91 times 1 over 2 to the 1 power, and that'd be 91 over 2, and that'd be 45 and a half. Okay, which is clearly not 13. So this would be out, and B is our solution there. Okay, and that's it. That's number 14. So yeah, I mean, I think as long as you're comfortable with linear and exponential, you do okay. And even if you're not, you can figure out the rate of change pretty quickly here. And I think most people would say, okay, this is definitely a growth. Yeah, and also there's actually no such thing as a linear decay or linear growth. No, that's not true, but usually these terms are associated with exponential. All right, let's look at number 15. Number 15, what do we got here? Okay. What are the solutions to this equation? So, personally, I think it's much easier just to plug these values in, see if they work. That's just how I would do it. So, there's other ways to do this, but I think plugging these numbers in is just the easiest way to do it. So 2 of these options have 0, 2 of these options have, and that's the only one that's common. Let's plug in 0 first. So 2 times 0, and then times 3 times 0 minus 4 equals 0. Well, 2 times 0 is 0, and then this is 0 minus 4, and then 0 times negative 4, and that's going to equal 0. So that one works. So neither one of these have 0, but yeah, we'll leave it like that for now. So we know this is these are going to be these are out. Okay, has to be one of these zeros. And technically, I guess there could be more than 2 answers if we didn't know our work. Well, they're not, but maybe somebody might think that. But no, cross those out because we don't have 0. So it's one of these two. So one of these is 3/4, one of these is 4/3. Let's plug in 3/4. So 2 times 3/4 times 3 times 3/4 minus 4 equals 0. 2 times 3/4 would be 6/4, and this would equal 9/4 minus 4. 6/4 is just 1 1/2. 9/4 is 2 1/4. Let's change it to decimal. I didn't give myself enough room. Rookie mistake. 1 1/2 times negative 1.75, and that is not equal to 0. We're going to stop there. 1 1/2 times that is not 0. So 3/4 is out. Let's just see if 4/3 works. So 2 times 4/3, 3 times 4/3, and let's see if that works here. So this is going to be 8/3, and then this would equal 4, because it would be 12 over 3, which is 4. These 3's also cancel, so 4 minus 4, and that equals 0. So 8/3 equals 0, times 0 rather, and then 0 equals 0, so that one works. So this is really, can you plug numbers in, honestly. There are other ways to solve it, but personally I think it's just the easiest way to do it. You could also set, like, I'll show you the other way you can do it. You could say, okay, we know these times multiply together equals 0, which means one of these two, one or both is equal to 0. So you could say 2x equals 0, solve for x. 3x minus 4 equals 0, solve for x. And you'll get it quicker. It's a faster way of doing it, but you have to understand how this works in order to do that. So if you don't know that, it's fine, you just plug them in. A lot of these problems, you can just plug things in, and it'll give you an answer. It'll give you the right answer. Sometimes it just takes longer, but oftentimes it's a reliable way to do it, okay? Okay, so let's see what we got here. Oh, I remember this one. It's a good one. Okay, so in a geometric sequence, the second term is 15, the fourth term is 135. What is the first term in the sequence? So we know the second term, a sub 2 is equal to 15. And we know the fourth term, a sub 4 is equal to 135. Okay. We do not know the third term, and we do not know the first term. Okay. Okay, so there's some key terms here. It's a geometric sequence, which means we are multiplying, right? We're multiplying by something. And we know that somehow we went from blank to 15, and then from 15 to another blank, and from that blank to 135. So we clearly were multiplying by an integer, not by a fraction, and not by a number between 0 and 1, because it's going up. So we have to think about this. All right, so if we start with 3, let's go through the line here. If we start with 3, I'm going to put a trial over here. So a sub 1, and this is when it's equal to 3, and this is going to take some time, but this is a way you can do it. So if I go from 3 to 15, right? Let's write this out here. If I go from 3 to 15, I'm multiplying by 5, right? And that's how I get to 15. So we have to have the number sense to see that. Or you can just divide 15 by 3 and realize it's 5. Okay, so let's multiply 15 by 5. So 15 times 5 is going to be 75. And then to multiply, I should change that color. If I multiply 75 by 5, I'm not going to get 135. 75 times 5, it's 375. So 3 is out. Let's try 7. This one's out. So a sub 1, a sub 2, a sub 3, a sub 4. So we know this is 15, we know this is 135. Okay, let's try 7. So to multiply 7 by something to get 15 is actually going to be, let's see, 15 divided by 7 is that number. If I write that as a fraction, it would be 15 over 7. And 15 over 7 times 15 is not 135, so you can already immediately tell you 7 is out. Let's try 9. So a sub 1, a sub 2, a sub 3, a sub 4. Okay. I know this is 15. I know this is 135. And you can see the value of scrap paper, guys, just by this problem alone. All right, so let's say it's 9. So in order to go from 9 to 15, let's see, 15 divided by 9, it's going to be 1 2/3, or 1.6 repeating. So multiply 1.6 repeating by 15. This is times, let's write this down here, times 1 2/3, times 1 2/3. This is going to give me 25. And multiply 25 by 1 2/3. That's 1.7. I get 42. So clearly that doesn't work either. So we know it's going to be B, but let's just show it here. So if I put in, actually go back to this, we're going to put in 5. All right, so 5 times what is 15? 5 times 3. And 15 times 3 is 45. And let's see if 45 times 3 is 135. Lo and behold, it is. So you can solve this really quickly with a good amount of number sense, but you can also write it out, okay? And you have to understand how a geometric sequence works. It's not an arithmetic sequence. The amount you're increasing by or decreasing by is not consistent, but the number you're multiplying by is. Okay? All right, let's see here. We're almost at the 20-minute mark, so I think we're going to stop there, and we'll pick up 17 in the next video. Okay, so hopefully that's helpful. Thanks, guys.